Okay, everybody, I'm going to get started. I'm not going to switch my video on, not because, for my main reason being that my internet connection up here at my home has been a little bit flaky, so I want to maximize the chances of me not dropping out during the session. So welcome to this webinar virtual tutorial looking at the software and hardware of ARCHER2. First thing I want to say is that please feel free to interrupt me with questions. That is, given the number of attendees we have, that is probably easiest to ask the questions in the chat, and hopefully I'll spot them, or one of my colleagues will spot them and tell me to stop talking and answer the question. If you prefer to wait to the end, hopefully I've really finished in plenty of time to allow for questions and discussion. Okay, so let's get started with this. So there's just a couple of preamble slides. One is that there's materials freely available and you can use it again if you want. The one I should mention, first of all, who the partners are for the ARCHER2 service, and that's UKRI, particularly EPSRC and NUMA, EPCC providing what are known as the service provision and CSE contracts, University of Edinburgh, who are doing the hardware and accommodation part, and Cray, who are a Hewlett-Packard enterprise company, who are providing the hardware itself. Okay. My final key slide is a disclaimer about the material in this presentation. So the final configuration of the initial ARCHER2 hardware and software is still in active development and still being worked upon. The information I'm going to present here is my own personal understanding of what the ARCHER2 service will look like and is based on information gathered from several sources. Any mistakes, misunderstandings, inaccuracies in this presentation are my responsibility alone and don't belong to any of the other ARCHER2 service partners, so don't blame them if it turns out that some things are different from what I say here when the actual service comes online. That's my fault entirely. Okay, so with that disclaimer, I'm hoping that I'm not actually going to be very far away from what the final configuration looks like when the service finally lands. The other thing I'm going to say is that obviously in the current situation, estimating timescales on when things will be available is quite difficult, so I have totally avoided any discussion of that. Also, I don't think I'll be able to answer in any concretely useful way any questions on timescales and availabilities. There will be communications out from UKRI, who are the lead organisation, as soon as that's available to send out to people. So, what am I actually going to talk about? So I'm going to start having a look at the hardware, in particular different types of nodes and the architecture, what we know about the interconnect so far, which is probably the least certain part of what we know about the hardware, storage, and as I go along throughout the presentation, I'll try and draw comparisons to the current Archer service, so you can try and see what's different and how it differs from the way Archer is set up at the moment. There's quite a lot of differences, mainly because Archer is very, very old now and it's been extended along past its original planned lifetime. So it is quite a big step change going from Archer to ARCHER2 in terms of technology. Then I'll talk a bit about the software, both the Cray provided software environment, which is the bit that comes along with the system, and the stuff that's going to be provided by the CSE service from EPCC, and again, comparisons to Archer. The idea here in this presentation was I wanted to give these details that will be useful for both users who plan to use pre-installed software on the service, people who aren't compiling their own applications but still need to know what the service looks like to be able to get the most out of it, and also users who plan to develop and compile their software on the service too, where particularly tuning and cache and what the compilers are in the development environments, debuggers, profilers, those sort of things are important to them. So I've tried to strike a balance between providing information that's interesting and useful to both of those types of user. So without further ado, we'll move on to look at the hardware. So this slide's based on the initial email that went out from UKRI about just an overview of the system, in that it's going to be provided by Cray. It's one of their new Shasta systems, and this is the sort of Cray marketing picture of a Shasta system. The peak performance is estimated around 28 petaflops, with various uplifts over Archer in the performance of the benchmark codes that were used during the procurement. In terms of, this is not a sort of core for core performance or a node for node performance increase. This is in terms of scientific throughput of the whole system. So it includes both the increase of performance of the hardware itself and also the increase in size of the system in these figures. So it's going to have almost 6,000 compute nodes in 23 cabinets and almost 750,000 core AMD cores in its final configuration. A large amount of Lustre file systems. As for Archer, there'll be a number of different file systems to provide some sort of redundancy or resiliency within the service. An addition on top of Archer that's not available on Archer is a large solid state, sometimes called burst buffer, but I think burst buffer implies one particular sort of use case, and that's not quite true here. This is much more general purpose, could be used for different types of use cases. And a large home file system, which is backed up. And all the nodes are linked together by Cray's new Slingshot interconnect. I found this nice picture on the internet of what the Shasta cabinets look like, which, although it is probably not particularly useful to users, gives you an idea of the high density of the system. So you can see all the various cabinets here with the compute blades slotting in. Everything is liquid cooled. You can see all the cooling manifolds going in there. What this actually means is that the density of the system is really high, and these racks are incredibly heavy. Really heavy, and there's a lot of there's work going on in the data center to provide floors with the strength to be able to support these density of racks for when the system finally makes its way to Edinburgh. Okay, but other than that, this picture was just interesting to show the scale of things rather than to provide any useful information. Okay, but a bit more detail on what the nodes are going to be available to users. All of the nodes have the same processor, which is the new AMD EPYC Zen 2 Rome processors, and they're the 7742 model numbers. So they have pretty standard clock speed for modern cores. There's 64 cores each. So that means each node, which has two of these sockets, two of these processors available, has 128 cores. Okay, so that's a big change from Archer, going from 24 cores per node up to 128 cores per node. And that also means there's the way it works out is there's quite a lot more memory available per node as well. One of the key things here, though, is that the login nodes, the compute nodes, the data analysis nodes, all these sorts of things are all exactly the same architecture and exactly the same processor. And one of the challenges when working on Archer in particular has been that the post-processing nodes are a very much older generation of processors than are available on the compute nodes and the login nodes. So you're always cross-compiling, and there's always a bit of confusion about why compiled codes didn't work the same on the post-processing nodes as they did on the nodes. Hopefully, in Archer 2, this will be less of a problem because the architecture is much more consistent across the system. Okay, so the login nodes have half a terabyte of memory and lots of cores available. The compute nodes are similar. The standard memory nodes will have 256 gig of memory per node, and the high memory nodes 512 gig per node. The memory is a bit faster, and we'll look in a bit more detail at the comparison of the compute nodes to Archer in a moment. There are also some data analysis nodes. These are equivalent to the post-processing nodes on Archer at the moment, and they are similar to the high memory nodes, with the idea, I think, that in the final configuration, people these will be shared nodes rather than exclusive, like the compute nodes. Okay, so there are the various nodes, all based on the new AMD processors, which are x86, so compiling and running stuff should work pretty well, because it's not a big change in architecture. It's still x86 compared to Archer. There is also what is known as the collaboration system. We know very little about this at the moment. There's going to be, we think there's going to be 2 nodes with 8 AMD GPUs. Not sure what that's for, or how it's going to be used, or how it's going to be configured, or what's going to be available on it at the moment. There'll be more information in due course once we have it going forwards. Okay, so I'm going to have a bit of closer look at the architecture of the compute nodes. Now, this is a picture of one of the blades that I also got off the internet. And on this picture, I think there are 4 nodes. So you can't quite see it, but the 2 copper plate bits are the 2 sockets. There's another 2 of them hidden underneath those integrated circuit boards that you can see on the top as well to make up 4 nodes in the blade here. There's 120 cores per node. There is what is known in Intel land as hyperthreading, 2 threads per core, hardware threads per core, so you can have up to 256 hardware threads on a node. There are 8 memory channels per socket, so there's a lot of memory bandwidth available, and it's fast memory. So you'll see on the next slide that the memory bandwidth is a lot bigger per node than it is on Archer. There are just over 5,500 standard memory nodes, and just under 300 high memory nodes going to be available on the system once it's installed. Okay, so doing a bit of a comparison between the compute nodes on Archer and the compute nodes on Archer2, I tried to list some of the features here down the left-hand side with a column for Archer2 and a column for Archer, and then did some sort of ratio calculation to try and show where the differences are. If the ratio is in green, then Archer2 is higher than Archer. If it's in red, then Archer is higher than Archer2. Okay, so as we've said, they're both dual socket. One of them's AMD based, one of them's Intel Xeon based Archer, but they're both x86. There's a lot more cores per socket and per node on Archer2 than Archer, which we've already mentioned. In terms of how many cores there are per NUMA region, well, on Archer it's 12 because the NUMA region's a socket. But on Archer2, this is more complicated because this is a configurable part of the AMD architecture, and we don't quite know what the configuration of the system is going to come in yet. So I'll talk a bit more about that in the next slide. The next line, which talks about the maximum single precision operations per second per socket or per node, is just a simple calculation based on the number of floating point units, the width of the floating point units in terms of vector operations, the frequency and the frequency of the processor, and the number of cores. Okay, and this is where the big difference is on Archer2 compared to Archer, is there's a lot more floating point performance available per node between the two compared to Archer. Okay, so that's a big change there. But actually, the change per core is not so big. So if you look on the next line, the change per core is not as huge, and what that tells you is that a lot of the performance uplift is coming from, or the floating point performance uplift anyway, is coming from increased numbers of cores per node, which is changing the balance of the system for different applications. So that's going to be something to be aware of when you're using the system. There's a lot more memory per node, which is great, which could be useful for applications, but actually there's less memory per core, and that again is because there's so many more cores per node. So the number of cores per node is increasing much faster than the amount of memory per node. There's more memory channels per socket, which should give more memory performance, more bandwidth, and actually more ability to access things concurrently as well. And the memory is a lot faster as well. So the memory performance should be higher as well. So if you look at the maximum memory bandwidth per socket or per node, then it's over 3 times higher on ARCHER2 compared to Archer, but actually there's less available per core on ARCHER2, less available bandwidth if you distribute it symmetrically on ARCHER2 than there is on Archer, again indicating the change in balance on the compute nodes between memory performance and compute and floating point performance. Okay, so the next slide continues the comparison a little bit more, looking a bit more at the cache and the NUMA regions. The caches is not hugely interesting. Mostly, and the caches are larger, or the L3 cache, the shared cache is larger because you've got more cores per node, essentially, and because you've got more floating point performance per core. So you need larger caches to be able to support that. So that just sort of flows naturally from the increased floating point performance. Now, the NUMA structure is more complex on EPYC than it is on the Xeon processors, where generally for Xeons you have 1 NUMA region per socket. That's how it's worked out. That's what it's like on Archer. There are 2 sockets per node, each with 12 cores. There are 12 cores in each NUMA region. But on the Zen architecture, each socket is actually made up of 8 core chiplets with a shared L3 cache. And these 8 chiplets are then connected together using what's called the Infinity I/O and Memory Hub chip. And this extra chip allows the socket to be configured to present different numbers of NUMA domains to the user. So you could have 8 NUMA domains per socket, which matches the underlying hardware very well in terms of 8 core chiplets. But potentially it makes it more complex to get the placement right, to get the right performance out of the system. There's various other combinations, and then at the other extreme, you can have 1 NUMA domain per socket, where the I/O and Memory Hub manages the cache coherency for you across the chiplets, and that comes at the cost, supposedly, of some lower performance in particular for some codes. I'm not aware yet, or I haven't seen in the public domain any measurements for real applications of what the impact of these different NUMA structures is. So that'll be something that we'd have to explore once we have access to the test system and could start porting codes and looking performance and things like that. As I said before, we're not sure yet what the configuration bit will be on Archer2, and actually, as I've just said, we're not even sure what the impact of the different configurations will be. So this part of the architecture is quite up in the air at the moment, and we'll have to see how it evolves as the system comes online. So in summary, for the compute nodes, which is what we've just been looking at, there's more compute power and memory per node, but the balance is very different. There's many more cores per node, and there's less memory and memory bandwidth on a per core basis, and there's potentially different cache and NUMA structure as well. So Electra asks, will the NUMA configuration be configurable by the user application? So I'm not sure. I have to say at the moment, this is something I get asked a few times. On the other test AMD systems I've had access to, it seems this is not available. It may be different on a Cray system, but generally I've not seen this available. I guess because it potentially requires a change to the BIOS configuration or a reboot of the node to change this. But we'll just have to wait and see. And of course, things may change over the lifetime of the service as well, depending on how software updates happen. So again, that's a bit up in the air. We just have to see how that pans out. So there's different cache and NUMA structure. I think what this sort of means, in any way on Archer and Archer2, the minimum resource you're going to be able to request is a full node. So we need to stop thinking about cores as the key resource indicator. And probably we should have done that a long time ago, actually, as higher and higher core counts came per node. Is you need to think about the whole node and how you can best exploit it. So potentially underpopulating the node, not using all cores to maximize things like memory bandwidth available to match to your application, and to explore more use of multi-threading per process, whether it's beneficial or not. Even if you get low benefit from multi-threading, it might be that that's just a bonus on top of having to underpopulate. We need to start thinking about how we use the nodes, because the balance is going to be different, and need to explore it for different applications. Also, because the system has a very different interconnect from Archer, and actually from a lot of other HPC systems, that might also change the characteristics of the balance between the nodes. So let's have my next slide, I think, is about the interconnect. Oh, yeah, here we go. So the interconnect's the Cray Slingshot interconnect, which is, instead of being an interconnect, well, the interconnect on Archer is based on ARES, which is Cray proprietary technology, and the interconnect on many other HPC systems is based on InfiniBand. The Slingshot interconnect is an Ethernet-based interconnect instead, supposedly high performance Ethernet-based interconnect. And unlike Archer, where there was a single network interface per node, so connected to one of the cores directly, there was a network interface that went out, which meant that if you were doing some sort of synthetic benchmarks, you could actually tell which of the sockets was connected directly to the interconnect and which one was having to hop across sockets to get to it. In this case, there's going to be two interfaces per node, one connected to each socket. Now, the actual performance of the interconnect is not hugely higher than Archer in terms of sort of the gross per node bidirectional bandwidth, for example. But this difference about how it's connected and how aware the interconnect is of which socket different, say, MPI ranks are running on, all these questions at the moment, and might change the characteristics of how the interconnect behaves and how that affects the balance of the compute power to interconnect power to memory bandwidth and those sorts of things. So this is the bit of the system I think we know least about at the moment, is how Slingshot's going to work. Can I say anything about the latency of the network? So Chris asks, no, essentially I can't. I couldn't find any real public information on that, and yeah, I couldn't find any numbers anywhere. So there was a interview with Steve Scott for Cray when Slingshot was first announced, which had the numbers around the bandwidth, and talked about the bandwidth, but he didn't really talk about the latency very much. I think, yeah, so my assumption is that to meet the benchmarks that we use during procurement, that the latency has to be at least as good as that on Archer, which is, I can't remember the exact numbers. I think it works out about microsecond latency, ping pong node to node, but I'd have to double check that. It's a similar topology to the interconnect on Archer, which is down to 3 Dragonfly, which is some sort of all-to-all like connection, but not quite. There's different layers. I'm not going to go into details of that. The thing it gains from being an Ethernet-based interconnect with this intelligent switches is that you can, as well as doing dynamic routing, which is what Archer does, what the interconnect on Archer does already, to try and avoid hotspots, it implants quality of service features, which are the sort of things that cloud providers use in their data centers to make sure everybody gets their fair share of network and moving data about. And what Cray have tried to do, my understanding, what Cray have tried to do, take those sorts of fair share quality of service technologies and bring them into the HPC interconnect, so that you avoid these like tail problems where one application could completely clog up the network, the interconnect for other people, or you can guarantee a quality of service for the I/O traffic across the network compared to MPI communications and things like that, to make sure that your system can achieve the right balance for the research on it. But as I say, know nothing about really the performance of this interconnect yet in the wild. I haven't seen any numbers on that. So we're going to have to wait until we get to the system and start doing some tests with applications to understand exactly how this works and what that means. Okay, so moving on to, that's all I had on the interconnect, not very much at all. Moving on to storage and I/O. So there are 4 just the file systems, sort of similar to the ones on Archer at the moment. We have 3 on Archer at the moment. They're much bigger than the Archer file systems. You can see in the table below that Lustre on Archer is about 4.4 petabytes, and we're going up to 14.5 petabytes in total on Archer 2. No backup of that, as is on Archer. There's a home file system similar to Archer, which is backed up for disaster recovery, going up from 218 terabytes to a petabyte. And there's the addition of this new solid storage, which is a Cray cluster store E1000F, about a petabyte of that. And that's going to be integrated into the scheduling system. So people can request that resource through the scheduler to use within their jobs. And I can't say much more about that either, because we don't know very much about that at the moment. And it's quite a new product from Cray, and there's not much public information out there at the moment, as far as I can find anyway. Particularly in terms, not so much in terms of the hardware, which you can look up, but in terms of how it actually integrates with the scheduler, those sort of things. That doesn't seem to be out there at the moment, as far as I can see. But I think rather than just burst buffer, it's more flexible than that. It can try to support lots of different types of use cases there, but we'll have to see how they balance out in practice on the service. Okay, so that's the end of my hardware. I had quite a lot on the compute nodes, because that was the thing I knew most about, and it has the most public information out there, and small amounts on the interconnect, because we don't know much, and a small amount on the file systems, because actually they're mostly not much different from Archer, and the only bit that is different I don't know much about, which is the solid state storage. So I'm sorry if it wasn't answering your questions there, but we used the information that I had available. So software overview. So as I mentioned at the start, I'm going to talk about both the Cray provided stuff and then have a little bit about the CSE provided bit. Just one slide on that, actually. The Cray software environment includes the Cray Linux environment, and the Cray program environment, which has various bits and pieces, which I'll talk about in a bit more detail in the next slides. Also, is going to provide support for Singularity Containers, and there are other features planned for future release as well, which I'm not going to talk about here, because that's in the Cray HP sphere of things, not mine at all. I'm going to talk about the stuff I know about from the public domain at the moment. The Cray Linux environment, as on Archer, I think is based on SUSE Enterprise Linux. So let's go to the next slide, if I can make that work. Next slide. Okay, so the scheduler and job launcher. So on Archer at the moment, where we have PBS Pro, on Archer 2, it's going to be SLURM instead. SLURM seems to be much more standard, I guess, around the world in HPC systems now, than PBS Pro, which you see less often. The other things to be aware of that are different from Archer is that there's no more AP run, which was the Archer equivalent of MPI exec or MPI run. Instead, now it's the native SLURM S run that's used to launch the parallel executables from your job script onto the nodes, or from your interactive job onto the compute nodes. The final thing to note, for some people who've used Archer may be aware of this or may not, is when you actually ran your job script on Archer, it didn't run on the compute nodes at all. It ran on these MOM or job launcher nodes, and then only the things that were launched with AP run actually went onto the compute nodes. Now, that's fine in some ways, but it caused some problems, because people typically want to do more in their batch script, in their job submission scripts, than just launch the parallel executable, or some people do anyway. So you might have a Python harness that does some calculations and then calls out to parallel jobs. Maybe it's doing some parameter space searching, maybe it's linked in with some ML framework or something like that, which is then launching the parallel executable. And they were always a pain to get running on Archer, because they would overload the MOM job launcher nodes, because they weren't designed for heavy compute, and if you had a few people doing something, it could put the service in danger. So those processes had to be killed, and it made it quite difficult to set up these sorts of more complex workflows. On Archer 2, the job scripts actually run on the first compute node out of the pool of compute nodes you're given. There's no job launcher nodes or MOM nodes anymore. So hopefully that should make these sorts of more complex workflows more suitable, easier to get running on ARCHER2. Which there's an example job submission script there. Maybe that is exactly what it'll look like, maybe not. It depends a bit on the configuration. Hi, Ash. Have you got a question?
Yeah, it was just to ask. That means that you're limited by the resource on that first node. So if you're launching something, you're limited by the memory or the processors on that first node.
Yes, but it's much closer to, I guess, what happens on all other non-Cray XC systems at the moment, which is that things are on the first node and your MPI exec then launches onto the other node. So it's much more familiar to people. And it's still an improvement over Archer, where the job launcher nodes could cause problems and there wasn't really a workaround. So yes, you're still limited by the resources on that one node for the stuff you're doing. If you want to do something different from that, you'd have to do something more complex. But it definitely makes things easier for
so it lets you set up the environment and everything as you want it. So I suppose that's a real plus.
Yeah. So, James, that's an interesting question, James. I don't know is the short answer. So the minimum request, yes, is one node, but whether once you're into that one node, you can use SRON to launch, I don't know, 128 single core jobs rather than as APU run, you couldn't do that. I don't know the answer to that. Is unfortunately the answer. And that I think we'd actually have to have access to the system and actually kick it a bit to see what happened. But that is an interesting point, and I will take note of that because that's something I hadn't thought of, and we should put into our testing to test that and see what turns up. Okay, so that's the scheduler. SLURM's pretty familiar to a lot of people who already use HPC systems, so hopefully, and it's pretty standard SLURM is my understanding, is that what you get on ARCHER2 is going to be pretty standard SLURM with nothing funny or new. The only bit that might be unfamiliar to people is integrating the solid state storage with SLURM, which is something that some sites do, but not as many as generally use SLURM. So compilers. There are going to be 3 environments provided by the Cray program environment. There's the Cray compilers, as on Archer CCE, which has their Fortran compiler, and the new Cray CC++ compilers, which are based on Clang. There is the AMD programming environment, known as AOCC. They have a Flang-based Fortran compiler and Clang CC++. And there's GCC with GFortran, GCC, G++. The biggest difference from ARCHER2, it obviously is no Intel compilers provided, because it's an AMD-based system and not a Intel Xeon-based system. So that may be a bit of a change for people who are used to using the Intel compilers, but GCC is pretty standard for most people now. And because Cray C is based on Clang now, that's much more standard as well. And the way the Cray program environment works, as you're probably aware if you work on Archer or on Isbar, which is a big Cray system that's available to UK researchers, is that all the Cray provided libraries and tools are within a program environment are guaranteed to work with all of the compiler environments that are available. Okay, so the other big difference for compiling anyway between Archer and ARCHER2 is that it's going to be dynamic linking by default on ARCHER2, whereas on Archer it was static linking by default. That's just something to be aware of. What that means is, I guess, that if you only use when you load software modules, if the program was compiled with an older version and then the default changes, then you'll pick up the new version when you load it. How do I recommend porting software from Archer to ARCHER2? Would you use your GNU? GNU is your compilation basis, Rash. So I think in some sense, yes, that's a useful default position. It depends on what people are doing on Archer. If you're already using the Cray compilers on Archer, for example, then I think shifting's pretty easy. Just carry on with the Cray compilers, and some people do that. If you're using the Intel, if you're based on the Intel compilers on Archer, then yes, it's likely that GCC is going to be the best place to go in the first instance when you move to Archer 2. Okay. I guess the main thing to be aware of is to not having Intel specific, is not to use any sort of Intel specific stuff, and not rely on that for your applications because for exactly this reason, you may get to a system where you don't have the Intel compilers, and that might be even more true in the future with the diversities of architectures that are coming up now. I mean, the U system in Japan is going to be is an ARM-based system based on the Fujitsu A64FX processors. There's no Intel compilers available there. Things are moving towards accelerators, and in some cases, Intel will have an accelerator, obviously, which will be supported by the intercompilers, but maybe you can't guarantee that both the AMD accelerators or the NVIDIA accelerators will have compatibility with the Intel compilers going forward. So being compiler vendor agnostic is definitely a useful thing to be with your HPC software. And of course, that's how it used to be, right? Back in the old days. I'm too old to, I'm older than I like to mention, but back in the old days, you achieved portability by having portable source that worked with all compilers, because you never knew if you were going to get access to a DEC chip, to an IBM chip, to an x86 chip, and the compilers were different for all of those things, and you had to be able to work with all of them. So compilers, that was the compilers. Next one, parallel scientific numerical libraries. So as for all Cray systems, the MPI is going to be provided by the Cray Message Passing Toolkit. So they provide a version of MPI and OpenSHMEM in that. And I think it also supports more esoteric parallel things like Cray Fortran, UPC, and also Global Arrays Toolkit that people occasionally use. Then the main vehicle for the sort of standard BLAS, LAPACK stuff will be the Cray libsci, which has BLAS, LAPACK, C BLAS, and LAPACK-E for C. People are using C, and BLACKS and SCALAPACK are built into it. There'll also be FFTW3 available. I think it used to be you had to provide FFTW2 for some codes that had used the old interface, but most of those codes have vanished now, and so I think the drop for the support for FFTW2 has been dropped from Cray stuff in general, and HDF5 and LTF, pretty standard I/O libraries, are going to be available too. There may also be other options for the numerical libraries. So Ash also asks how compatible the Cray message passing libs with GNU compiled code. Is there OpenMPI or OpenMP? So they're perfectly compatible with GNU compiled code because the library is independent of the compiler, and the Cray guarantee that all the compiler environments that they provide are supported by all the libraries they provide. So that cross-compatibility matrix just works. OpenMP you get from your compiler. So from the Cray compiler, you'll get the Cray OpenMP, and from GNU, you'll get GOMP, and so on and so forth. I think from the AMD stuff, you'll pick up the Clang OpenMP implementation. I don't know what they use, whether they leverage GOMP or whether they have their own thing. I need to look into that. OpenMPI, I don't know. So Cray MPI is based on MPitch and supports MPitch, the ABI, the Abstract Binary Interface, I think that stands for. So if you compile MPitch code, other MPitch code on a different system, you can load a module on the Cray system and it should work, right? Okay. It's a bit more technical than that, but it should work. So you should be able to compile with MPitch somewhere else and then run on the Cray systems. But how easy that is to make work, then I don't know. We'd have to test in practice. Slingshot is quite new, but I have a feeling it's based on open standards down below, so something like libfabric or something like that. So there is the potential probably to compile a version of OpenMPI for Slingshot. I don't know what the performance would be like, but that's certainly an interesting thing if you could look at and see how well that worked. Right, where are we? So that was the scientific parallel library. So the other thing that's new compared to Archer, and this is partially because it's been in the Cray provided software for a while now, but hasn't been there, but is new to Archer users because Archer is quite old, is Cray provide versions of Python and R. So they provide a Python free distribution which has NumPy, SciPy, MPI for Pi, and Dask built in. I went and had a play on Isambard, who do have these bits and pieces already, and it seemed to work that you could just use pip install ---- user to build on top of the Cray Python distribution. So that all looked quite good. That Cray R I know less about. That's mostly because I'm not an R user, so I know less about R. So it was hard for me to understand what's available and what's not. I had to look at what packages were available within the Cray R distribution. They're all the standard ones plus parallel. What I don't know is if that parallel works across multi-node or whether it's just parallel within a node at the moment. And as I said, there's not that on Archer. So this hopefully should be a useful addition to the stuff available on ARCHER2 for users. Profiling and debugging, I'm going to skip through these things quite quickly. There's various debugging tools. The big difference from Archer that at the moment on Archer we have ArmForge DDT and ArmForge Map for debugging and profiling respectively. Neither of those are going to be available on ARCHER2, at least initially. But in terms of profiling, CrayPat's a pretty good tool and really useful. I have less experience of GDB for HPC, which is a command line GDB version built for parallel debugging, or Valgrind for HPC, for HPC memory debugging. But we'll learn more about those once we actually get the system. In terms of containers, this is a key thing that we see lots of requests for in Archer at the moment, and of course Archer sold that the Linux kernel sold it can't support containers properly, so we don't have containers on Archer. But on ARCHER2, Singularity Containers are going to be available from the get-go to allow people to provide custom environments, particular applications, workflows, support for legacy and custom versions of software without having to maintain the whole caboodle on ARCHER2 itself, capturing environments to enhance reproducibility, potentially making software complex dependencies easier to install, or at least shifting laxity off you to someone else is probably a better way of putting that final one. And as I say, nothing of it, these aren't available on Archer, so hopefully we think this is going to be a really useful feature to people. And I know that Cray have been doing some testing with the Singularity containers to try and get recipes together for being able to use them with MPI on multi-node for multi-node jobs. So Singularity with MPI for multi-node jobs, as well as single node stuff. So final slide, essentially on software. So in terms of the CSE service software environment, we're still working on this, getting this together at the moment. We obviously don't have the system or even the test and development system to try installing and port things to. So it's a bit up in the air, but there will be the modeling and simulation research software installed essentially, a subset of that. For example, VASP, Casta, OpenFOAM, GROMACS, the sorts of applications that are heavily used on Archer. We'll add some additional scientific and numerical libraries, depending on what the communities want. So things like PETC, Boost, Eigen, those sort of things, maybe, and some other things. Data analysis tools and software, there's some on the radar, the NetCDF operators and the climate data operators, NCO and CDO. I've also got an aspiration to install VisiData. If you haven't seen what VisiData is, you should go and Google it, because it is data analysis in ASCII. So go and have a look up at that. I'm desperate to install to see if that will work on ARCHER2, and other software as required by users. The initial set's going to be based on the analysis of the use of Archer, what people have been using there, and consultation with the scientific consortia, the NUMA and EPSRC scientific consortia, to get the base set in place. But that doesn't. But it's obviously going to evolve over the lifetime of the service. There's also plans for the major software packages to have training courses associated with them, which is a bit different from Archer, where we haven't focused on specific software packages so much. On Archer 2, there's going to be more focus on that to provide training to allow people to get the most out of really the big heavily used packages on the system. So I think that is just about me. So in summary, Archer 2 is pretty new technology, right? So there are new cabinets, the Cray Shasta ones, it's relatively new processors, the AMD EPYC Zen 2 ROMs, a very new interconnect, the Cray Slingshot. The balance of the compute node in particular is different. There's much more floating point power available per node and total memory per node, but maybe not so much on a per core basis. So the efficient use is going to provide some more investigation and some it's going to be a learning experience. The CSE team obviously will get access to the test development system as soon as possible and start those investigations and put up their initial sets of advice as soon as they have them for people, so that at least you're not starting from ground zero, hopefully, in most cases. And also, you know, if you're not on the major software packages or you want advice or have questions, then you can always contact the service desk, and the CSE team will be able to get back to you and help you out. There's going to be a solid state storage component available to potentially improve the I/O performance for some applications, or allow for different workflows or making workflows more efficient. Again, there'll be more information on that in due course. Hopefully I've shown you there's quite a broad research software stack, from the sort of basic tools of compilers and numerical libraries up to the full software packages that can be installed, but also support for some things we haven't had on Archer, or better support for things we haven't had as much of on Archer, Python, R, containers, things like that. But the good news is the environment's going to work in a similar way to the current Archer setup. So the Cray module environment looks very similar and hasn't changed hugely. So it should be pretty familiar to most people. In fact, probably, I think the biggest initial difference most people experience with the system is nothing to do with the hardware or anything like that. It's going to be going from PBS to SLURM. It's going to be the probably the biggest step for a lot of users, or the biggest change for a lot of users anyway. So the Archer 2 website's up there, ARCHER2 AC UK, and we're currently in the process of drafting some initial documentation, which we're going to make available pretty soon. And yeah, we'll just keep adding stuff as we learn more about the service. So I'm happy to answer any more questions people have. I hope you found that useful and or interesting, or at least one of those two things. So Chris has asked, could I comment on the expected target workloads for Archer 2? Beefy individual nodes make the systems more amenable to shared memory workloads, but will the system still be mostly targeting large distributed memory applications? So the answer is yes, the main target is still capability computing. So the main difference, or one of the major differences between Archer 2 and other HPC systems available, is the high performance interconnect across large numbers of nodes. So the type of jobs you can run there that you can't run elsewhere are going to be the big parallel distributed memory capability things. Obviously, there's also the ability, or that also gives you the ability to have some sort of higher throughput for more loosely coupled calculations, so for metadynamics or for extracting different input parameters and things like that. So there is the potential for that mix and everything in between. So there's that potential for the mixture of throughput with high parallelism as well. But the main target is still capability computing. Doug asks, is the old hardware being donated somewhere? The answer is, I think actually no. I think Cray are taking it away. It's probably going to be scrapped. I mean, it's really old now. I mean, they're Ivy Bridge processors, so they're ancient, and plugging in a Cray XC is not just they're not standard racks. So plugging it into an existing data center is quite a challenging thing to do. Mike asks, You mentioned 18 times speed up for the Do you have any details on the config that was used there? So that was, it's in the Archer benchmarking repository, but HadGem 3, I think, was the model type that was run there. I'm not a UN expert, so I don't know quite how to express the details, but HadGem 3 was what was used. Ash asks, will there be template scripts for SLURM to transition from PBS scripts? Yes, one of the key bits of the documentation will be example scripts. It is interesting, actually. That raises an interesting point. Maybe we could write a little tool that would do some sort of conversion for users, so they could just give it a PBS script and it would give the equivalent in SLURM. That might be an interesting thing to explore. George asks, will the RDF be mounted on ARCHER2? I think the short answer is the plan is yes. Not exactly sure how and in what configuration and which nodes yet, but yes. And Andrew C asks, you mentioned single precision floating point performance. How double precision? Well, the single precision I mentioned was just a back of the envelope relation from based on what you know about the processor architecture. You can translate those numbers into double precision just by halving them. Should we be investigating more mixed precision floating points? I think the general answer to that is yes, that's an interesting thing to explore, and understanding how the scientific output of applications varies with things like changes in precision and also changes in various input parameters. So sensitivity analysis is a really important thing, and is going to be much more important going forward as architectures diversify. I'm also being asked, can you give some information about early access and how to apply? The short answer is no, sorry, though we're still awaiting those details. They'll come out from via UKRI and the research councils about the way to get access. Because we don't know the date of delivery yet, actually, that's a little bit moot at the moment too. Keith's asking, is there any help for data migration to ARCHER2? The short answer, I think, is that the RDF is the place to go if you've got space on stuff on Archer and you want it on ARCHER2, given the RDF is going to span both systems. Putting it on the RDF to then copy back will be. We're not planning to copy across any data on the work file systems. We are investigating possibilities for what we can do around the home file systems between Archer and ARCHER2, but nothing's there yet. Ian says there's already packages that accepts many PBS scripts. Cool, I'll have to play around with that then. And Alan says RDF mounting ARCHER2 depends on relative timings. Okay, so maybe I was a bit strong in my statement then. And there's another thing about the Rosetta Stone for workload managers. Thank you for that link, John. I will go and look about that. Doug says, how do we request software for installation? Same way as on Archer is you mail the service desk, and the CSE team can help you out. We'll discuss with you what the requirements are and how best to meet them. And Ash says read-only mounting of home between Archer and ARCHER2. Maybe we're investigating possibilities there. I can't say any more than that. Phil asks, is the ECSE timetable still as advertised? So the short answer for me is yes, the advertised dates are still the current dates, as far as I know. I don't think there's any changes planned to that, but keep an eye on the CSE page and notifications coming out from the service. Thanks, Alan, for confirming. So 19th of May is advertised for the first ECSE call. Okay, so once again, thanks for everybody who came along and listened, and yep, stay safe, and I hope you enjoy the rest of your week.